Hello, my name is Alex Almanza. Today is March 3rd, 2021. Welcome to video presentation 1 for ECPE 170. Let's just get right into it. All right, so here on my right, we have a very simple, bare bones little program to make a 6-row by 8-column array, counting up by 1. This program should count from 1 to 48 with 8 numbers in every row. However, here in the main function right here, just to simulate any kind of operation on array elements, I've added 10 to each element individually. So instead, we're going to count from 11 to 58. We accomplish this with 4 functions. Int build array, which is allocating the memory needed to build this 2D array. Fill array, which is just filling the array with elements from 1 to 48. Printing the array, which is printing the array. And then free array, which is deallocating all the memory that we allocated back in build array. All right, and then just to confirm real quick how I copied the files from the Bitbucket repository to presentation1 was cp main.c makefile presentation, if I can spell it right, presentation1. Easy peasy. And then obviously to make the directory before we did that, I did make dir presentation1, like that. Let's go ahead and move to presentation 1. Both files are in there. Okay. So the first question for any kind of program is the question of how we'll be able to compile it. That's accomplished in the command line through the use of this makefile, which I have opened here. Makefile essentially automates compiling, just so that way we don't have to enter a huge command every time we want to compile our code. Makefiles can definitely look extremely intimidating, but are usually pretty standardized. So the main thing to note here is that this line, cc equals gcc, specifies our compiler, which is gcc. C-flags enables a bunch of different compiler options, namely -c tells gcc to only compile and not to link our code. -wall enables error messages to be printed to the console whenever we compile. -standard equals C99 is just our language standard. -g is important for something that we'll do a bit later when looking for memory leaks. Finally, the -03 enables compiler optimization so that our code runs a little faster. We have no headers, but any and all .h files would go right here. For any .c file that we have, we need a correlating .o file if we want that to be compiled in the final executable program. The rest of this is essentially just settings that are combining all of our generated object files and smashing them together into our targeted output file, denoted by this -o, into our executable. Finally, we have this clean option down here. This adds an optional command that we can use to remove any generated .o or executables. Okay, finally, we can compile our code using the simple command make. And then to run it, all we need to do is /program, because that's what we named our executable. And we can see it right there in green. And then if we want to time how long it takes for our program to run, all we need to do is time./program. And then the most important thing here is just the real time, which is just how long it actually took to run the program. All right. Now, let's break it. We're going to intentionally cause our code to create a segmentation fault, a very common error that occurs whenever our program tries to access a memory address it isn't allowed access to. Doing this is unfortunately very easy. Here in print array, I'm just going to change rows, which is assigned to 6, to the number 10. So that will try to print 10 rows and 8 columns. So we'll just go ahead and recompile, try to run it, and then we'll get a segmentation fault. What's happening here is that we tried to print 4 extra rows when we only allocated enough space in build array for 6. So we'll just go ahead and change that back. And then let's go ahead and try to do another nasty error. Let's try to get a memory leak. All we have to do for that is to comment out this line free array. So when we make, oops, I need to save it. When we make and run it, nothing happens. However, what's happening in the background is that we're getting a nasty memory leak. So over here, I saved this big long command, and we'll just go ahead and paste that in. And so what this is doing is this is running our program, our executable, through Valgrind's memory checker tool and making a log file called memcheck.txt, which is just what we called it. So if we list the directory, we'll see it right there. If we open it, it'll just look like a bunch of mumbo jumbo. But what we're looking for is this leak summary. So according to Valgrind, we definitely lost 48 bytes, which we did. We tried to, or we allocated enough space for a 48 element array, but then never freed it. So we definitely lost 48 bytes. And then up here, we get 2 lines in main.c that Valgrind is printing out. Main.c, line 34 and line 36. If we go back, we'll see that line 34 is where we allocated space for our rows. Line 16 is just a function call. What Valgrind is trying to tell us is that we allocated space for that array, for this size, but never freed it, essentially. So to fix that, all you have to do is just uncomment that again. Okay, now pushing files to version control is also pretty simple to remember. Rule of thumb, your routine will always be add, commit, push. And then just for fun, you usually want to get status between. I already pushed everything, so I'm not going to do it again. I don't want to clutter up my commits. But this get status will essentially print out, as a matter of fact, I could just do it over here. It'll print out a little, basically what you've modified, what needs to be added, that kind of thing. However, before you ever add anything to the repository, you always want to make clean. So now you should see we don't have any .o files left or the program executable. And that's just about it. Thank you.